Imagine your desk is completely covered in books, and you need to bring out a new one to study. You have to put one back on the shelf to make room. But which one do you pick? This is the exact problem operating system face when RAM runs out of space. Today, we are looking at how the OS handle this using two replacement algorithms, which is least recently used LRU and clock. First up is LRU. It looks backward in time. Based on the principle of temporal locality, it assumes that if a page hasn't been touched in a long time, it is safe to kick it out.
Let's trace it using our new sequence. Page 2 and 3 arrive first, easily filling the empty slots. Next, the system requests page 2 again. Since page 2 is already in memory, this is a page hit. Now eviction happens, but notice how page 2 shuffles the front of our mental line as the most recently used. Then, page 1 arrives and fills our last empty frame. The real magic and the eviction happens when page 5 arrives. Memory is completely full. LRU looks backwards in time to find the oldest page. Even though page 2 entered the memory first, it was reaccessed recently during our page hit. Page 1 was just loaded. The page has set either the longest age exactly page 3. Therefore, LRU evicts page 3 and replaces it with page 5. While LRU is mathematically brilliant at minimizing these page faults, it has a massive real-world catch. It requires a heavy hardware overhead to constantly track the exact timestamp or access order of every single page.
Because pure LRU is too expensive for actual hardware, operating system use a low overhead approximation called the clock or second chance algorithm. It organizes memory frames into a circular buffer managed by a moving pointer called the clock hand, where each frame carries a single use bit 0 or 1. When a page is accessed, its use bit flips to 1. When a page fault occurs, the clock hand sweeps through the frame to find an eviction candidate. If it encounters a 1, it clears the bit to 0, giving that page a second chance and move on. It continues spinning until it finds a page with a 0, which is immediately evicted and replaced.
Now, let's quickly trace how this works with our reference string. In steps 1, 2, and 4, pages 2, 3, and 1 arrives and simply fill up our empty frames, setting their use bits to 1. However, step 3 gives us a page hit because page 2 is already there. Notice that the clock hand stays completely still on a hit. The main event happens in step 5, when the page 5 arrives. Since memory is full, the clock hand has to spin through all the frames. It clears everyone use bit from 1 to 0, giving them all a second chance until it loops back to frame 1. Since frame 1's bit is now 0, page 2 is evicted and replaced by page 5. Finally, in step 6, page 2 comes back. The hand is pointing at frame 2, which has a bit of 0. It gets no second chance, so it's instantly replaced by page 2.
To wrap everything up, let's look at a quick side-by-side comparison of these two algorithms across three metrics. First, core logic. While LRU exactly identifies and evicts the single page untouched for the absolute longest period, clock acts as smart approximation of this behavior using a circular array and a simple 1-bit second chance flag. Secondly, for hardware and overhead, LRU requires a high overhead because the system must constantly update timestamp or shift active lists on every single memory reference. Clock, on the other hand, keeps overhead exceptionally low by requiring just one reference bit per physical frame slot. Finally, for implementation complexity, pure LRU is highly complex and financially expensive to support in high-frequency modern memory management. The clock algorithm provides a beautiful alternative. It is simple clean and straightforward to program directly into hardware or OS kernels. Ultimately, while LRU is a great theoretical goal, the clock algorithm is what makes efficient page replacement practical in the real world.
That's all from us. Thank you.